paper and a pencil, and pitter patter, let's get at her. So we're going to start this morning by trying some practice problems from chapter 3. So this is the acid-base chapter in our textbook, and we're going to start by looking at question 3.34. And I've noticed that I think some of these questions are pretty quick, and then some of them are a little bit longer. So the question just says, draw the conjugate base of all of these acids. So draw the conjugate base. That's all we're asked to do. So say, for example, we're starting out with ethanol, okay? Ethyl alcohol or ethanol. Well, we're asked to draw the conjugate base. What is a base, right? A base is a proton acceptor, right? And if these are all acids, right, what is an acid? An acid is a proton donor. And so since this is an acid, right, everything that we're given in 3.34 is an acid, it's going to donate a proton, an H plus donor, like that. So where's the most acidic proton? It's this one here that has a pK of around 16. So when that compound donates a proton, this is the conjugate base you'll be left over with. And you can draw it like that, or you can put in all the lone pairs like this. So all we're doing is we're removing a proton, right? So let's assume we have this acid, and this is a ketone. This is called cyclohexanone. That's neither here nor there, but you should know what a ketone is. So we have a variety of protons on here, don't we? We have these protons here, we have these protons here, and then we have protons down here, right? And I'm just labeling one. Of course, there's two protons here, and there's two protons here, and there's, right, so on and so forth. But could anybody tell me which one of these would be the most acidic proton, the red, the blue, or the green? Because there is a difference between them. Which one? Yeah, it's the red one. Why? Because when you remove the red one, right? You remove the red one, this is the conjugate base, right? And what's so great about that conjugate base is that it's resonance stabilized, right? You end up with a resonance contributor that looks like this, okay? There we go. And if you were to remove the other protons, if you were to remove, let's say, the blue proton or the green proton, the carbanion that you would be left over with would have the negative charge on a carbon, of course, right? Just like this one. But if you think about areo, right, you couldn't differentiate between those three protons using A, but you can using R, right? Because the red one, when you remove it, it has a resonance contributor, where if you removed either one of these, the blue one or the green one, you would not get a resonance contributor. And so there you go. We've drawn the conjugate base of that acid. Now, the next one, C, is ammonia. Now, ammonia is a base, right? When I think of ammonia, I think of it being a base. However, it can behave as an acid, right? Because this question is asking us to draw the conjugate base of the following acid. So, you know, it depends on the situation. Sometimes ammonia can behave as a base, and that's probably most of the time. But sometimes it can behave as an acid. It can donate a proton. Could anybody describe to me or type in the chat? And I realize it's not easy always to describe these kinds of things over Microsoft Teams. But could anybody tell me what the conjugate base would look like, or name it, or anything? It is a base that we've seen throughout chapter 3. We talked about it a few times yesterday. So if ammonia donates a proton, right, what would I be left over with? What would be the conjugate base of this acid? Okay, if you're unsure, it might help. Yeah, exactly. Autumn, you're totally in the right place. Yeah, it's the amide ion. So NH2 minus is what you end up with, right? If you're unsure, right, you could draw the Lewis structure of ammonia, which looks like this, right? If that was to donate a proton, you lose H plus. Like, let's say we have a base. Okay, I'll just call it B. Okay, well, let's say we removed that proton. What would you be left over with? You'd be left over with the nitrogen with the lone pair, these two hydrogens, and then you'd have another lone pair, right? This is the Lewis structure of NH2 minus. Think about the formal charge. You have nitrogen, which has 5 valence electrons, subtract 2 sticks and 4 dots, which gives you -1. Therefore, there you go. So you end up with amide. So this is called the amide ion, okay? Amide ion is what we would call that. So that's the conjugate base of ammonia. What about hydronium? right? If we were to write out the structure of hydronium, or just write out the condensed formula, H3O plus, could anybody tell me what the conjugate base of hydronium would be? What would you be left over with after hydronium? Yeah, absolutely. I knew my students would be really quick on that one, right? That's something that you would have seen Avogadro's number of times in general chemistry 1 and mostly in general chemistry 2, right? So you'd be left over with water. Absolutely. That's what happens when hydronium donates a proton. Let's try another one. If we have this carboxylic acid, I know obviously we haven't studied carboxylic acids in depth, but you should know that when you draw carboxylic acid, this is the acidic proton in the carboxylic acid. So when we donate that proton, what's it going to look like? We're going to be left over with the oxygen. Sorry. We're going to be left over with the oxygen. Go. But now it's going to have a negative charge. So again, we haven't covered carboxylic acid nomenclature whatsoever, but this is a carboxylic acid that you would have seen, many, many times in general chemistry. Could anybody identify this carboxylic acid? Again, it's one that would have shown up a lot in general chemistry 1 and general chemistry 2, especially when you talked about weak acids. It's a very common weak acid. No, if there's nobody's got a guess on this one, I'll tell you because it's going to show up a lot. Yeah, Bruna, you got the name of the conjugate base. Absolutely. Okay, so the acid, this is called acetic acid, right? It's the major component of vinegar, acetic acid. And then this is called the acetate ion. Okay, and the reason why I know that you would have seen this is because when you would have learned the Henderson-Hasselbalch equation, you remember that for determining the pH of a buffer, you used what? The pKa plus the log of the conjugate of the concentration of the conjugate base divided by the acid. You would have seen this as an example many times. But now that you're all organic chemistry students, you should know what acetic acid is because you see it so much in organic chemistry. So after that carboxylic acid, acetic acid donates a proton. We're left over with this conjugate base, which we call an acetate ion. Again, I'm not going to ask you to name a carboxylic acid, but it's food for thought. Let's try a couple more. What if we had this guy? So if we have this, this is an amine, right? Just a plain old amine. And we learned about functional groups. Well, this is the proton that we're going to lose. Now, remember, this nitrogen already has a lone pair on it, right? Nitrogen always has 3 bonds in 1 lone pair when it's neutral. So if that was to lose a proton, and I'll just draw, let's pretend we have a base, and I'm just drawing a generic base. This is something organic chemists do all the time. They'll just draw B with a lone pair and say, there's your base, okay? It's going to abstract that proton, and then you put the lone pair down here. And so the conjugate base would look like this. You have nitrogen with 2 lone pairs, okay? And there you go. This is called diisopropyl amide, and it's a base that comes up, now and again in organic chemistry. Let's try one more. Could anybody name this ion NH4 plus? And it's not a trick question. What's NH4 plus called? Everybody should be Johnny on the spot with their polyatomic ion. Yeah, Autumn, you got the conjugate base. You got that down, Pat. Could anybody name this ion? Ammonium. Thanks, Warren. Absolutely. That's the ammonium ion. There you go. So you take ammonium, and when ammonium loses a proton, you end up with NH3, which is ammonia. All right, there we go. So we practiced drawing some conjugate bases from some acids, and we saw how you can even think about something that's basic, in water, like ammonia. You can think about it as being an acid, okay? We saw an amine, right? Amines are bases, but in certain situations, they can behave as an acid. They can donate a proton. Let's move on from there and take a look at question 3.35. And the question asks us to draw the conjugate acid for each base. Okay, so we're given a bunch of bases, and some of them might be abundantly clear that they're bases, other ones maybe not as much. But we're going to start with A. So if we have a carbanion like this, okay, it's missing a proton, right? If we add a proton to it, okay? Because remember that a base is a proton acceptor. So after this accepts a proton, what are you going to be left over with? You're going to be left over with 1, 2, 3, 4 carbons, okay? So there you go. Can you clarify what you mean, Jessica, about the nitrogen?
I thought it was supposed to be positive on that, because isn't it
Which one?
for F?
No, because when you remove a proton, right, you'd end up with the base taking on a proton. So the base would become positively charged, right? You generate a conjugate acid like this. But when you look at the formal charge of this nitrogen, you have 5 valence electrons, subtract
Yeah,
1, 2, right?
I see
Subtract
it now.
2,
Yeah.
subtract 4, and you have -1. It's the exact same thing that we did here, okay? Whenever nitrogen has, so that's one of the bonding patterns that we looked at in chapter 1, I believe. Whenever nitrogen has 2 bonds and 2 lone pairs, it's got a negative charge, all right? There we go. So let's go back here. So there we go. So that's butane. It's the same butane that's in a butane lighter or a butane curling iron if you like to do your hair out in the forest or something where there's no electricity. The next one is the conjugate base of a ketone. So we have a negative charge here. So if that gains, right, if that gains a proton, so all we're doing is we're adding H plus to all of these. What are you going to end up with? You're just going to end up with the ketone, right? There you go. So you're going to end up with the ketone. All right. Next, if we have C, we have sodium amide. So NaNH2, that's called sodium amide. It's an ionic compound. Well, sodium is a cation. It's a spectator ion. So when you throw acid at this, it's not going to do anything to the sodium. However, right, this is minus, this is plus, right? When you throw H plus at this, you're going to protonate the base to make ammonia like that. So there we go. D is we have water. Could anybody tell me what the conjugate acid of water, when it behaves as a base, what that would look like? And it's not a trick, okay? It's one of those things you hear me say Avogadro's number of times throughout the class, right? I hate trick questions. There you go. So we end up with a hydronium ion. What's the next one? The next one is, this is isopropanol or isopropyl alcohol. This is rubbing alcohol. The same rubbing alcohol that you can buy down by the pharmacy counter at Costco. They sell giant bottles of it for peanuts. Anyhow, if we want to draw the conjugate acid, right, who would be the proton acceptor here? Right, think about it. We've got a lone pair, 2 lone pairs on the oxygen of the alcohol. So if we treat this with H plus, right, which is what we're doing in all these problems, right, the alcohol is going to accept the proton. And then let's draw what we'd be left over with. You still have these 3 carbons. You have the oxygen. You still have the first bond to hydrogen. You have one of the lone pairs, and then you have another bond to hydrogen like that. Could anybody tell me what the formal charge in that oxygen is? Yeah, it's +1, absolutely, right? Because whenever oxygen, right, one of the bonding patterns for oxygen is whenever oxygen has 3 bonds in a lone pair, it's got a positive charge. There we go. So there's our conjugate acid of the alcohol. Let's try one when we have an amine. So the next one, this is called propylamine or 1-propylamine or whatever. Anyhow, there we go. If we treat this with H plus, who's going to take the proton? Well, we have a lone pair on the nitrogen, right? So that's going to accept the proton. Then we're going to be left over with 1, 2, 3 carbons, and then we have our nitrogen. But instead of having 2 protons on it, now it's got 3 protons on it. So now the nitrogen has a +1 charge. That's the same thing as drawing this, right? If we drew the nitrogen, we draw 1, 2, 3 bonds to hydrogen, right? And then we put our positive charge like that. It's the exact same thing. The next one is an interesting one that pops up quite a bit in organic chemistry. If we have a ketone and we treat that with an acid, who's going to accept the proton? Well, we're going to start with the lone pair on the oxygen. That's going to accept the proton, and we're going to end up with a conjugate acid that is something that was in our table, right? In table 3.1. This is called a protonated carbonyl. I guess you could call it a type of an oxonium ion. Anyhow, does anybody remember what the pKa of this proton is? It was in table 3.1. I'm testing you on your table 3.1 skills. Does anybody remember the pKa of this proton? This proton right here that I'm highlighting in yellow. No? Okay, yeah, it's minus 7.3. Yeah, it's really acidic. Okay, so the pKa here, the pKa of a protonated carbonyl is negative 7.3. Very acidic. Okay, HCl is negative 7. Okay, so you see that that is very, very acidic, and that's going to come up over and over again in organic chemistry. The last one is kind of a funny one. I know you would all nail this one. Is sodium hydroxide, right? So sodium is a spectator ion, but when you put hydroxide in acid, what are you going to get? You're going to end up making water, right? The sodium is just a spectator, right? And sodium hydroxide is an ionic compound. There you go. All right, let's take a look at question 3.36. I picked out some ones that I thought were just interesting. So question 3.36, and I can't write down the whole thing, but I can describe it to you. It says you've got compound A, and it's got a pKa of 7, and you've got compound B, it's got a pKa of 10. Could anybody tell me how many more times acidic compound A is than compound B? How much more acidic is compound A than compound B? How many times? Is it 1 billion times, 1 million times? It's 1,000 times, isn't it, Kyla? Right? Absolutely, right? Because the difference in pKa here, the difference in pKa is going to be 10 minus 7, which is 3. Every log unit or every pKa unit is a multiple of 10. So this is the same thing as 10 to the power of 3. What's 10 to the power of 3? It's 1,000, right? So compound A is 1,000 times more acidic. It's not 3 times, it's 1,000 times more acidic. 10 to the power of 3. Okay, let me look at my notes here. A bunch of problems. Let's try question 3.39. And we looked at a question like this yesterday. And if you don't have your book open, I can kind of help you out here. It says in question 3.39, it says nothing more than would ethanol be a good solvent for this reaction. Okay, and the reaction is this. We're taking this alkyne and we're treating it with amide, right? NH2 minus, and we're making the conjugate base of the alkyne, that's called an alkanide, plus ammonia. Okay, if we evaluate the pKa's, right, this is our acid, this is our base, this is our conjugate base, and this is our conjugate acid. So if we evaluate the pKa's, the pKa of this is 25, and the pKa of ammonia is 38. So yeah, the equilibrium is going to lie to this side if we could do this reaction, but that's not the question. The question is, would ethanol be a good solvent? Could anybody answer that, yes or no? If anybody was studying last night and maybe could answer me, could you do this reaction in ethanol? Ethanol is cheap. Okay, it's a very cheap solvent. You don't have to break the bank. Yeah, Jessica says no. I tend to agree with you, Jessica, right? Why would that be? Why wouldn't it work? Because if you think of what would happen, if you have a reaction flask and you have both of these in it, and you try to dissolve it in ethanol, okay, which we'll just abbreviate like this, ET. So ET means this, CH3, CH2, and we'll see that later on today. But if you try to put that in ethanol, I guess I'll draw the bond line structure. It's not going to work, right? You're going to destroy the solvent and you're going to destroy one of the reagents. Why? Because what's going to happen is your ethanol, draw the structure here, plus your NH2 minus. Let's say this acted as an acid. What would you end up with? You'd end up with ammonia plus the conjugate base of ethanol. Well, if we evaluate their pKa's, the pK of ethanol is 16, and the pK of ammonia is 38. Whoa, Nelly. The equilibrium is going to lie completely to this side. that means you're going to destroy all of this. There's going to be none left. Okay. So there might be some ethanol left over because you're going to put this in there in excess, but all of this is going to be destroyed. So bye-bye base. Okay. You're not going to get that reaction occurring. So ethanol would not be an appropriate choice. So the answer is no, because this is going to happen, right? In the same vein, let's take a look at question 3.40, which is in the same vein. It's not the same question, but it's asking you, could you protonate this base, and this is called a benzoate. If you look at the ingredients on foods, you'll see benzoate, sodium benzoate in it. So this is sodium benzoate. So with water, could you protonate this with water? You know, and if you're unsure, this is how I would do it. I would say, I'll draw that base, okay, the benzoate ion. So let's draw that out. And then if we were to put that in H2O, hypothetically, you know, if we just draw equilibrium arrows, what would we end up with? We would end up protonating, right? Because water would behave as an acid. Okay, so will this work? Will I be able to protonate this and make this compound plus hydroxide? If we evaluate the pKa's, the pK of water is 15.7. The pK of a carboxylic acid is around 5. So we'll just put pKa equals 5, right? And the thing in the table, it says 4.75, whatever, close enough. So which side is the equilibrium going to lie to? Well, it's definitely not going to lie to the side of the products, is it? It's going to lie hard to the side of the reactants. Why? Because we always lie to the side of the weaker acid, right? It's 10 to the power, it's almost 10 to the power of 11 more acidic, or sorry, less acidic than this, okay? And so, no, water is not going to protonate it. It's not going to make that. So the answer here is no, okay? Not going to work. So you have to be able to choose appropriate solvents. Give me a thumbs up if you follow me on that one. If you don't, let me know, and I can try to re-explain it. If not, we'll move on to another problem. Okay, don't be afraid to stop me at any point if you're like, I don't understand this, or could you re-explain that? If we've got time, I'm more than happy to do it. Let's try question 3.41. 3.41. I just want to try B and C. It just says, draw an equation for the proton transfer that occurs when each of the following acids react with water. Okay, so we'll say draw curved arrows for reaction, which I'll abbreviate like that, with water. This is a real chemist's shorthand. We just write reaction. I don't know why, but here you go. Okay, reaction, just RXN, a lot faster. So in B, we're looking at sulfuric acid, right? H2SO4. This is just the Lewis structure. I'm going to leave the lone pairs out for now. But what happens if we put that in water? Right? Sulfuric acid is a strong acid. So it's going to donate a proton. It's going to do its job. So what's going to happen is the water is going to accept the proton from the sulfuric acid, right? Remember, sulfuric acid is a proton donor. That means that water is going to be a proton acceptor, and that's what it's doing right here. It's accepting this little guy, that little proton, and so what are you going to be left over with? Well, you're going to be left over with this. You're going to be left over with hydronium, the hydronium ion. Here we go. And you're going to be left over with hydrogen sulfate. So the hydrogen sulfate ion, like this. Now, if you're wondering, why did you draw the equilibrium arrows like that? Let me repeat myself again. The pK of sulfuric acid is -9, and the pK of hydronium is -1.7, something like that. So the equilibrium is going to lie to the side of the weaker acid. So it's going to lie to the side of the products. Let's try the next one. The next one is one we're going to see come up a million times in this class, and that's where we start with that protonated carbonyl. Right, remember, we just discussed this a few minutes ago, and we said that it has a pKa of -7.3. This thing is really acidic. It's just as acidic as hydrochloric acid. Okay, that is acidic, my friends. Hydrochloric acid is a strong acid. So what's going to happen if we put this in water? Right, if we put this in water, is that it's going to be a proton donor, and the water is going to behave as a proton acceptor. right? So it's going to take that proton, then this pair of electrons is going to end up back on the oxygen, like that. I'll draw my equilibrium arrows like this. I'm going to end up with my ketone intact, and I'm left over with the hydronium ion. I'll just draw H3O plus like this. The pK of the hydronium ion, again, is around negative 1.7. So that's why the equilibrium is going to lie to the right. It's going to lie to the side of the product. There we go. Let's try one that, question 3.47. We did 3.44, didn't we? 3.47. It says, this is 3.47, my friends. If you want to see a classic question in organic chemistry, look no further than question 3.47. This is one of those questions that shows up on every standardized exam, every final exam. I'll probably put it on the quiz. I haven't finished the quiz yet, but I'll probably put it on there. So we have hydroxide, we have the acetate ion, which I showed you earlier today. So that's again called the acetate. We have, oops, draw a better line than that. We have the T-butoxide, okay? And then we have an ethoxide like that. Anyhow, even if you couldn't name them all, and you should be able to name these two for sure, the hydroxide and the acetate. These ones you could just call them alkoxides if you want. But what it says rank them in terms of increasing basicity. So we're going to go from least basic, okay, basic to most basic. All right. So how would we do that? Okay, how would we do that? Since we don't know what the pKa's of these conjugate bases are, but we know the pKa's of their conjugate acids, don't we? Right? We can, just from our table 3.1, we know the pKa's of all the conjugate acids. So here I'm going to write pKa of conjugate acid. So the conjugate acid of hydroxide is water. It's 15.7. The conjugate acid is acetic acid, which has a pK of around 5. The conjugate acid here is tert-butyl. This is called tert-butyl alcohol. It's got a pK of 18. And then the conjugate acid here is ethanol, which has a pK of 16. So what was the rule? We said the stronger the acid, the weaker the conjugate base, right? So least basic is going to be the conjugate base that results from the strongest acid. Therefore, we're going to put the acetate ion as the weakest, right? It's the wimpiest one. It's the weakest base. It's the conjugate base of the strongest acid. And from there, we just go upwards. So after that, it's going to be the hydroxide ion because its conjugate acid has a pK of 15.7. Then we keep getting weaker acids as we go to the conjugate base of ethanol, which is the next weakest acid. Then we go to the weakest of all the acids, which is T-butanol, like that. Oops, I meant to put the conjugate base in there. There you go. All right, so there we go. We go from least basic to most basic. And again, how did we do that? We didn't use Areo, did we? No, we had to have a working knowledge of table 3.1 in our brains in order to solve that problem. Give me a thumbs up if you at least follow me on the rationale. I'm sure you might be saying, well, give me a little bit more time, with table 3.1, we just discussed it yesterday. But, once I have that table down, Mr. Dion, I'm going to be able to do this kind of problem and kill it, just ace it. Okay, great. Good. These are important types of problems. I'll put a star by this one. This is a real chestnut, a real classic in organic chemistry. They always love to ask this question, rank things in order. In fact, I don't have the ACS final memorized, but I know in organic chemistry 2, a couple semesters ago, I did the ACS final before the pandemic, and we were looking at some practice questions, and that was one of the questions was rank these, in terms of basicity or acidity or something like that. Okay, let's try question 3.48. This is the last one that I wanted to look at. And of course, I want you to take a look at all of the practice problems that I assigned. And again, they're not assigned for points, but I just suggest that you look at. What would you call it? Strong suggestion, maybe? A strong suggestion. So this is question 3.48. So we're getting in some good practice here. And this question asks us, identify the most acidic proton in a compound. Okay, so you're given this compound, and all you have to do, maybe all I got to do, I'm going to move that down, is identify the most acidic proton. That's it. Now, this is not the easiest thing, or some of them might not be the easiest to describe the answer over Microsoft Teams. But just looking at compound A, it's a bifunctional compound. It's got, an alkyne and an amine in the same compound, kind of an interesting molecule. Could anybody tell me which proton here, or describe which proton would be the most acidic? Even if you have a guess, this is a safe space. Don't be afraid to just take a guess. If you think you have a hunch or something. If we think about all of the all of the hydrogens in this molecule, right? This one here is, somebody says all the way to the left, Mackenzie, right? So this proton all the way to the left, the one on the alkyne, we know has a pKa of around 25. Right? We know that the pKa of the proton on an amine is, right? I told you last class it was around the same as the pKa of ammonia. So even if it's just close to a pK of 38 or something like that, okay? Well, there's a big difference between 25 and 38, right? That's 10 to the power of 13, okay? So that's a huge difference in relative acidity, right? This is way more acidic, okay? What are all the other types of protons in this molecule? Every other proton is from a sp3 hybridized carbon hydrogen bond here on these three carbons. Those are all going to have pKs of around 50. And so the answer is the proton on the alkyne here. This is by far the most acidic proton. And this question is a very important question because you're going to train your eye to be able to look at molecules very quickly and assess, which proton is the most acidic. Let's try another one. And before I want to get into this next question, I want to say another thing about A, is that A could not be solved using Aereo, okay? Aereo will not work to solve this problem. If you remember this particular example where you have an amine and a terminal alkyne, that's the exception to Aereo. So this is exception to Aereo. You'd actually have to solve this one using table 3.1. If you tried to solve it using Aereo, you would assume that this conjugate base would be more stable and therefore that would be a more acidic proton, but you'd be wrong, okay? So again, Aereo works most of the time, but I went over this exception many times in class yesterday, at least 2 or 3 times, where you have to use table 3.1. You have to use pKa values to solve this problem A. Well, let's take a look at B. We got 3 functional groups here, right? We've got a thiol, an alcohol, and an amine, all in the same compound. Could anybody solve this one and tell me which one would be the most acidic proton if I was to maybe highlight these in yellow, this one in red, this one in green, something like that? Anybody have a inkling about which one would be the most acidic? Well, let's think about these for a second. What are the ones that we know from table 3.1? We know that the pKa of an amine proton, right? We know the pKa is around 38, and we know that the pKa of an alcohol, let's just say it's around 17, okay? It said 16 to 18, but anyhow, let's just say it's around 17. Well, if you remember when we looked at Aereo, right? Aereo, okay? And we talked about the acidity of an alcohol versus a thiol. So this is called a thiol, right? That's a functional group that you had to learn, a thiol. So a thiol, if we look at group 6A, we go from oxygen to sulfur to selenium to tellurium, then down to polonium, which is neither here nor there for this class, but anyhow, right? We know that atomic size increases going down, right? Size increases. And the bigger the atom is, the greater the ability it will have to stabilize the negative charge, right, that results when it loses the proton. And so when you're comparing a thiol versus an alcohol, a thiol is going to be more acidic, right? Because the conjugate base, the dominant factor when we're comparing elements in the same group or family is size, and sulfur is bigger. And in fact, you can maybe try and memorize this, that a thiol has a pK of around 7. And so you could have solved this, again, using Aereo, okay? Or you could solve it using pKa's, because I told you this pKa yesterday. And so the answer is the thiol is the most acidic of all. So maybe you could put that in your, in your toolbox, right? An alcohol has a pKa of around 17-ish, something like that. And a thiol is quite a bit more acidic, okay? It's around 7, and that's based on the size, right? Oxygen versus sulfur. Sulfur is a much bigger atom. Okay, there we go. Let's move on to the next one. This is just looking at a compound that's comprised of nothing but carbons and hydrogens. So just a hydrocarbon is what we call it. We've got this molecule here. And this is tough to answer without me highlighting some protons. So why don't I do it like this? I'll draw this proton, and this proton. And I'll highlight this one in green, this one in yellow, and I'll highlight this one in blue. Could anybody tell me which one of these would be the most acidic proton? The one in green, yellow, or blue? There's one here that's more acidic than the rest, quite a bit more acidic. If we think about Aereo, right? Atom, resonance, induction, orbital. If we were to draw the conjugate base that would result from the abstraction of any of these 3 protons, the negative charge would be on the atom, on the same atom. It would be on a carbon for each one of them. But I can solve this using resonance. If I give that to you as a hint or a clue, could anybody tell me then which one would be the most acidic? There's only one of these protons that if you removed it will produce a resonance structure or a resonance contributor, or will be stabilized by resonance, however you want to frame it. Only one of them. And this is going back to chapter 2. Which one of these protons, if I ripped it off, would give me something that I could draw a resonance contributor for? There's only one proton here that I could
Blue.
rip off. Go ahead.
Blue.
Yes, good. Okay, I was going to wait until somebody answered that. Because if you were to draw this compound, like this, I'll just draw it like that, and I'm going to copy it. And I'll paste it over here. Okay, and then I paste it over here. Okay, if you were to rip off the one in green, okay, you would end up with this, okay? We don't form carbanions on sp2 hybridized carbons. That's really unstable. If you were to rip off the one in yellow, same thing. We don't form carbanions on sp2 hybridized carbons. Highly unstable. If you rip off the proton in blue, you end up with this. And you can draw a beautiful resonance structure for this, right? You end up with a resonance stabilized negative charge or carbanion. And there you go. Now you can draw this resonance structure where you have the double bond here, you have the lone pair over here. Okay, so this is the kind of rationale you need to have when you're studying organic chemistry. Even my brother, who works in business, even he had to admit that organic chemistry is logical. It is a very logical subject, but you got to think. The answers will not always be abundantly clear, right? You got to really concentrate sometimes in organic chemistry. Let's try another one that's in the same vein as the last one. This is D. I'm going to draw this big old molecule here. It's bicyclic compounds. We have 2 rings fused together. We have a ketone over here. We have an alkene here. We have a methyl group here. We have another methyl group here. We have this group over here. So I'm just going to label a few protons. If I had this one, or this one, or I'll put this one in yellow. Or if I had this one here. Okay, I've got a blue proton, a red proton, a yellow proton, and a green proton. One of these is more acidic than the others by a lot. Can anybody tell me which one of these would be the most acidic proton? Right, we got to think about the conjugate base. You look at each one of these protons that I've identified, they're all bound to carbon, aren't they? Each one of them is bound to a carbon. So if you're thinking about aereo, you can't solve it using atom, can you? Cannot solve it using atom. You've got to use something else. If I was to try and solve it, or if I move down to the next thing, which is resonance, and that's how we're going to solve this problem. If I pull off the proton in blue, am I going to get a resonance contributor? No, absolutely not. If I pull off the proton in yellow, I would end up with a carbanion on an sp2 hybridized carbon. Absolutely not. That's highly unstable. If I pull off the proton in red, I do get a resonance contributor. Okay, I would get a resonance contributor if I pulled that one off. Okay, and I see that a lot of people are saying it's the red one. Right? If you were to pull this off, okay, you end up with this carbanion, and yes, you can draw curved arrows that show resonance like that. So you have two resonance contributors, right? You're done there. The buck stops there. I'm going to go back. What if I pulled off the one in green? Okay, if I rip off the one that's in green, I end up with this carbanion. I can draw one resonance structure that's going to look like this. Oops, I put the double bond there when I didn't mean to. So I'm going to have a negative charge here, a double bond here. So I'm going to end up with this resonance contributor like this, but I can also draw a second one. Here we go, and here we go, like that. Okay, so I not only have one resonance contributor here, but I have a second one. The second one is going to look like this. So this part remained untouched. Now we have the double bond here, and we have the negative charge on our oxygen here, and there we go. So the answer is the one that I had highlighted in green because there are two resonance contributors. The one in red, there's only one, but the one that I had highlighted in green has two resonance contributors. So we have the overall resonance hybrid represented by these three structures. All right, there we go. Let's skip E, and I want you to, of course, look at that one. Let's skip ahead because I want to get into chapter 4 today. Let's take a look at this one here. Could anybody identify the functional group in this compound that I have drawn here? Could anybody tell me what functional group is in here? So what functional group is in this one? All right, it's an aldehyde. All right, remember aldehyde, aldehyde, okay? So spelled with a Y. So aldehyde. You know what the most common spelling mistake of chemistry students is this, and I'm sure that none of you would ever do this, is this. That is the most common mistake that I see, is students spell fluorine like this all the time. Not in organic chemistry because we don't talk about fluorine that much, but it's fluorine, not flowering. It's fluorine, not flowering. The students love to write down, it's flowering. There you go. So an aldehyde. So if I was to say, I don't know, identify a couple of protons here. Oops, where's my pen? I have this one and this one. Let's say I highlight this one in blue, I highlight this one in yellow, and I highlight this one in green. Could anybody tell me which one of these protons would be the most acidic? If we were to remove the one in blue, so if there's something I want you to remember for the rest of your lives, okay? If you were to remove the one in blue, you would end up with this. Okay, you'd have a negative charge on an sp2 hybridized carbon. In organic chemistry, you're never going to find a negative charge. No negatives on on sp2 carbons. Never. Okay? If you ever draw a negative charge on an sp2 hybridized carbon, you know you've done something wrong. Okay? I'm never going to ask you a question where you're going to have that. If you remove the one that's highlighted in yellow, however, you would end up with this. Right? You'd end up with this, where you'd have a negative charge here. And what's interesting with that negative charge is that it's resonance stabilized. So we can draw a resonance contributor here, which is going to look like this. So we have our negative charge up here. There we go. So we've got resonance contributors here. And if you remove the one in green, if you remove that one, you've got this, this, and this, but there's no resonance stabilization. So in terms of aereo, right, the negative charge is on a carbon in each thing that we drew here, but you solve it using resonance. So the yellow one has a resonance contributor, and therefore it is the most acidic. Okay, remember this: you are never going to find a negative charge on an sp2 hybridized carbon. If you see something like this, okay, if you ever draw an aromatic ring and you've got a negative charge like that, generally speaking, we don't see that. Now, if you're like, we see something similar to it in organic chemistry too, but the only reason we draw it is just to help us rationalize a structure. But if you ever have a double, like an sp2, and you've got a negative charge on it like that, or if you've got, a carbonyl and you've got a negative charge, none of these, okay? Get that straight. You'll never see those in organic chemistry. No negative charges, right? What are these carbons? That's sp2 hybridized carbon, right? That's an sp2 hybridized carbon, right? This is an sp2 hybridized carbon. You can't put a negative charge because the way it looks like you can't put a negative charge on an sp2 hybridized carbon, okay? Never, ever, 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 ever will you ever, 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 ever see that. Okay, I got one more question. We're going to do this really quick. I want you all to nail this one. Okay, if I have this compound, what's more acidic, the red proton or the yellow proton? Give me the fastest answer you got. It's the red proton, right? You can solve it two ways. You can solve it using aereo, okay, because a sulfur is bigger than an oxygen, and they're both in the same group. But I told you that the pK of a thiol is around, we'll say around 7. pK of an alcohol is around 17. So literally 10 to the power of 10 times difference probably. It's a huge difference, my friend. What's 10 with 10 zeros after it? That would be, so if you have a million, then a billion, so it'd be 10 billion times more acidic, right? All right, there we go. So that's a little bit of review of chapter 3.